All right, let's next talk about adjacency, the adjacency matrix representation. And an adjacency matrix is a lot of times the most natural for students to use. It's not the simplest, which is why I like to start with edge lists, but adjacency matrix makes a lot of sense as well. So how does that work? Well, for each row in the matrix, it represents all of the connections to a given vertex. So you can think of this as everything connected to vertex 0. So vertex 0 doesn't have an edge connecting to itself. There's no sort of self-connection there. But it is connected to vertex 1 through this edge. It's not connected to vertex 2. So you can think of this as 0, 1, 2, 3. And then as you go down the column, is the current vertex connected to this vertex? So is 0 connected to 0? No. Is it connected to 1? Yes. Not connected to 2, 3, or 4. Not connected to 5. It is connected to 6. Not connected to 7. It is connected to 8. And that's how the adjacency matrix representation works. So that's row 0. The second row is for the next vertex, and so on. So if you were to correspond this matrix to this graph, or you could basically draw this graph from this matrix. A couple of interesting points I want to make here. The first is that you could represent this as true-false value. So you can represent each item as just a bit, which gets you a really compact representation. A lot of times we just represent it using a byte or an integer. And if you have an undirected graph, it will be symmetric. So for example, if vertex 0 is connected to vertex 1, vertex 1 will be connected to vertex 0. If vertex, let's see, 0, 1, 2, 3, let's pick something out of this one. It's connected to 0, 1, 2, 3, 4. So vertex 4 should have one at 0, 1, 2, 3. So it will be symmetric around this diagonal. Unless we have self-connections, the diagonal will be 0. Otherwise, anything that's sort of on the mirrored side will show up on both sides of the diagonal here. All right, so which one is this? This would be 3 to 8. So if I go down here to 8 and I look at 3, those two correspond to each other. Okay, so given this adjacency matrix representation, how do we count the number of vertices and how long does it take? Well, we just have to return the length. We just have to return the length of the adjacency matrix itself. So the length is essentially how many rows are there. And this is an n by n matrix. So it's just a constant time operation to get the number of rows in the matrix. Next, how do we count the number of edges and how long does that take? Well, to count the number of edges, we do have to do some work here. So the simplest way to look at this is for non-weighted graphs. All we're going to do is say for each row in the adjacency matrix, sum across the row. So for example, if we take this row and we take the sum across it, we'll end up with 1, 2, 3. So there are 3 edges connected to vertex 0. And if we do that for all rows, and then take the sum of all rows, that will tell us how many edges there are. Of course, we do need to divide by 2 for an undirected graph, otherwise we'd be double counting edges. Next, how do we add vertices and how long does that take? Well, adding a vertex is not the most natural operation here, but essentially what we need to do is we need to add a new row and a new column. So I always find it easier to start by adding the new column to everything. So we'll add an item here, here, basically add an item for each row. We just append an item to it. And the default value could be something like none if it's a weighted graph, or it could be, for example, a 0 for a non-weighted graph. And then we add the new column. So we count the number of edges and then append a brand new row to the adjacency matrix. All right, how do we add an edge? Okay, well, to add an edge, we first have to check to see if there's an edge weight. And that'll make it easier to destructure and pick out the vertices. So if there is no weight, we'll just add a weight of 1, and then we'll eventually just sort of ignore that weight value because it's just 1, and it'll just say, okay, that edge now exists. Just a simple little way to make that code a little cleaner. Alright, so what we're going to do is we'll first say at the adjacency matrix at v1, v2 is equal to that weight. So it's 1 for a non-weighted graph, and it's going to be the weight value for a weighted graph. And if it's not a directed graph, we also do the symmetric position, so v2, v1. That's a constant time operation. We're just basically changing 1 or 2 values. So we, for example, could be changing this one and this one, or just this one for a directed graph. Okay, how do you check for the existence of an edge, and how long does it take? Well, finding an edge is sort of the opposite of adding an edge. It's still just a constant time operation. So if our graph is weighted, we just want to make sure that that location is not none. Otherwise, we're going to return whether or not it's 1. So that will tell us whether or not that edge exists. We just check that one location, and we do that in constant time. All right, next, how do you find all neighbors of a vertex? All right, well, for finding neighbors, we just have to loop across a given row. So the important thing to look at here is we're going to loop over all vertices that are in a specific row. So we're going to look at the row V. So for example, this row here. And we'll just compare each value to the default value. So if it's a weighted graph, we'll compare it to none. If it's a non-weighted graph, we'll compare it to a 0. And if it's not that default value, we will append it to neighbors and then return neighbors. And since we're looping across a row, that's going to take us linear time. All right, next, and finally for adjacency matrices, how much memory is needed to store the graph? Okay, so to count the amount of memory, well, we have to know how many vertices there are. We have to know how many bytes each one of these cells takes. And then finally, it's an n by n matrix, and we just multiply that by how many bytes it takes. And each byte, again, depends on whether or not we're storing things as a bool or a float. And that's basically saying, is it a weighted graph or an unweighted graph?